All right, we're continuing on here, chapter 14, acid bases. Oh my. So obviously we talked a little bit last time about a couple things. Again, a reminder, we talked about our Bronsted-Lowry definition. Again, a proton donor, which is our H plus, is an acid. A proton acceptor is going to be our base. And as we talked about last time, again, you want to make sure that you think about it as H plus, as the positive charge does obviously affect the overall charge of whoever is losing it or gaining it. And as we talked about, obviously, if you lose a positive charge, you become one more negative, and if you gain a positive charge, you become one more positive. And our relationship, as we talked about as well, again, we have our acid and base on the left-hand side of the arrow, and we do have our conjugate partners on the other side. And we have our conjugate base and our conjugate acid. And again, the relationship here, acid on one side, conjugate base on the other, and base on one side, conjugate acid on the other. And once again, the Bronsted-Lowry definition of an acid is it's going to send our H plus over. So that one single H plus, as we talked about, is the only difference that you could have in order for these things to be considered sort of pairs of partners. And as you go from the acid to the conjugate base, it will have one less H plus as it has given it away. And as you go from the base to the conjugate acid, we'll end up with one more H plus as it accepts it. And again, can only be that one H plus difference from them to be related to each other in that sense. Which we talked about a little bit, I think, last time as well. Again, if you have a diprotic acid, something like sulfuric acid, again, each of those hydrogens do come off one at a time. And that is why, for example, H2SO4 and SO4 2 minus are not considered partners, as it is a two hydrogen difference between them. The thing that ties those guys together is the HSO4 minus in the middle, and those are partners for each of those things. We got into really an equilibrium with water, which is amphoteric, and water can react with itself. And water will break apart into H plus and OH minus and set up an equilibrium. And because it does set up equilibrium, we could write an equilibrium expression for this, which is known as Kw. And that is the concentration of the H plus times concentration of OH minus at 25 degrees Celsius, which is probably 99.99% of the time when you're going to use this sort of value. It has a value of 1 times 10 to the minus 14. As we also mentioned last time, it is really an equilibrium expression. And as we know, temperature does affect the value of it. So if you happen not to be at 25 or they make a special note of it in a problem or something, you may actually use it maybe a different value for KW. But like I said, almost 100% of the time, that's going to be the value you're going to kind of roll with in most calculations. What this allows us is, again, we can compare really our acid part of the solution to the base part of the solution. And the relationship again between H plus and OH minus is a opposite relationship. So as one goes up, the other goes down, and vice versa. So if our H plus concentration equals our OH minus concentration, then we do have a neutral solution, pH of 7. If our H plus concentration is larger than our OH minus, so our acid part is greater than the base part, then it's going to be an acidic solution. And if the base part, which is the hydroxide, is greater than the H plus, it will be a basic solution. So you could calculate the H plus concentration, the OH minus concentration, compare the two, and help you determine that. The other thing we also obviously talked about a lot is, again, H plus and H3O plus are interchangeable. So again, this is the same formula basically, where we just kind of use H3O plus instead of H plus. So again, you can interchange both of these guys, as we talked about, kind of in formulas or in equations as well in that sense. Any questions on that? Definitely, as we also probably mentioned last time, you want to make sure you are using your exponent button when you punch these things in on your calculator. Otherwise, you're going to be pretty far off on a lot of calculations along the way if you're not using proper scientific notation when you try to punch this into your calculator. Any questions on any of that there? All right. So I think we left off with this example. So why don't you give it a go? In solution, we have an H plus concentration of 1.2 times 10 to the minus 6. What is the hydroxide concentration, and is it acidic, basic, or neutral? Let's give it a go, see what you come up with. Yeah. I meant 14, but yeah. It's like invisible ink. There you go. That's 14. There you go. The H plus concentration, we're looking for the OH minus concentration. And 1 times 10 to the minus 14 there. In this case, we are given the H plus concentration. The good news is it's really the same calculation regardless of which one you're given. You're going to take to solve for the opposite one, you take 1 times 10 to the minus 14 divided by our 1.2 in this case, times 10 to the minus 6. That is going to give you an 8.3 times 10 to the minus 9. It does need units of molarity as it is a concentration. If your calculator is not in scientific notation, you probably got like 8 zeros and an 8 at the end because you ran out of room, basically. Yeah. That's okay too if you got the 8. So, but if you put in scientific notation, you'll get 8.3 times 10 to the negative 9. It just rounds there because it runs out of room, basically. First off, any questions on the calculator there? Okay. So now we want to compare. So we basically want to compare our H plus concentration to our OH minus concentration. And in this case, which one's larger? It is the H plus concentration is larger. A reminder that when you're comparing negative exponents, the smaller negative exponent is actually the larger number. And that's because you're only going that many places to the left and putting zeros, right? So it makes it a larger number. So that would mean H plus is bigger, so we'll go with acidic in this case. Yeah. Questions on that there. Okay. So let's talk a little bit about pH and measuring pH. So the pH is a measure of acidity, and we use the pH scale to help us determine. And the pH scale runs from 0, bless you, to 7 to like 14. And below 7 is acidic. Above 7 is basic. And technically speaking, right on 7 there is neutral. And as you go from 7 towards 0, you're becoming more acidic. And as you go from 7 towards basic there, you are 14, you're becoming more basic in this case. So to calculate the pH, that's the formula I just wrote right through. So I'm going to rewrite it again here. pH is equal to minus the log of the H plus concentration. And this is also, again, another one where if you want, you could just substitute in H3O plus in that case. And again, means the same thing. So depending on your calculator as to how you want to punch this in, if you have a display calculator, you're going to punch it in exactly the way it's written, which means you're going to hit your negative button. You're going to hit your log button, and then you're going to put your number in, making sure you probably use your exponent button if you're doing that. If you have a non-display calculator, you're going to actually go backwards. So you're going to actually start with the number, then you're going to hit log, and then you're going to hit your negative button. If you're not sure what type of calculator you have, just hit the log button. And if it says log, congratulations, you have a display calculator. If you hit log and it says error, congratulations, you have a non-display calculator. Yeah, so that's a quick way to figure out which one you got there. Now, as the H plus concentration increases, the pH decreases, and vice versa. So more H plus, more acidic, lower pH. That happens in this case. Now, if you have a pH that is, again, less than 7, it's going to be acidic, and you will have a greater H plus concentration. If you have a pH greater than 7, you're going to have a greater OH minus concentration. And why we call pH of 7 neutral there, it is going to be a concentration where H plus equals the OH minus concentration, and that is 1 times 10 to the minus 7, which will give you a pH of exactly 7. So for our class, we're going to go with 7 on the nose there as neutral. If it's a little bit above 7, a little bit below 7, we'll call it slightly acidic or slightly basic in that case. But a pH of 7 is going to be neutral in this case. Any questions on that there? Say it one more time. Exactly, yeah, they're equal to each other. So, yep, and that's why again a pH will be 7 at that point. Let's talk a little bit about pH and sig figs. So when you calculate something like a pH sort of value, the number of decimal places in the pH value is equal to the number of significant figures in the concentration value. So, for example, we had an H plus concentration of 1.2 times 10 to the minus 4. Why don't you calculate the pH here and see what you end up with? Okay, so if we calculate again, punching it in whichever way you need to do that, you should end up with something on your calculator that hopefully looks like you'll have something like 3.92081.875 and a bunch of other numbers probably. At this point, my answer should be what? 3.92. 3.92 should be my answer in this case, and that is because this concentration has 2 significant figures. Gives me not 2 significant figures, but 2 decimal places in this case. So you're going from significant figures to decimal places as you go from concentration to pH. By the way, we'll talk about going backwards, and if you go backwards, then you're going from decimal places to sig figs if you're going back to concentration, if you're going in the backwards way. This obviously would be acidic in this case, yeah. Any questions on that there? All right, so there is our pH scale, and again, as you can see, we have some strong base there in the basic range, strong acid, some other acids. We have pure water here, which is a pH of 7. This is a pH meter, which is a nice old-fashioned Beckman one there who invented it. It measures the H plus concentration flowing around in that solution, basically. And really what you do is it measure voltages. So you calibrate it with a pH of 4, 7, and 10. It makes a little calibration curve and then goes, cool, this voltage is a pH of this. And it kind of does it that way. If I took water that was been sitting out, will it be a pH of 7? It actually will be probably down in this range, believe it or not. And again, because it will pick up some CO2 from the air, make some carbonic acid, increase H plus concentration, bring it down a little bit, more acidic than it would be and stuff. That's why years ago, before they moved in that fancy building you're in now, they used to make you boil the water when you did that titration experiment in Chem 50. Because we were back in building 11, not very sealed building. So you used to have to boil all the water before you made your sodium hydroxide solution to get rid of the CO2 and all that kind of stuff to it down. Nowadays, they don't have to do that. They build the buildings a little more tightly built than years ago. All right, so let's talk a little bit about some similar scales to pH, and that is the POH. And the POH is calculated very similar to the pH. The POH, very much like the name implies, tells you what you need. You need OH minus, and it is the minus the log of the OH minus. So the pH minus the log of the H plus, POH minus the log of the OH minus. Why would you bother with that? Well, there's a nice relationship between those two, which is if you take the pH plus the POH, it will add up to 14. And that means if you have the hydroxide concentration, you could calculate the POH first and then subtract 14 to get to the pH. So you could kind of go back root it as well. So there's a few things here. We have our pH. We also have our KW. So you may not even need to use KW in certain cases, as we'll talk about here in just a second. There are a few things. A couple of things, though, before we continue on here about the POH scale. It also runs from 0 to 7 to 14. The difference is it runs opposite of the pH scale, which means you're below 7 here, you're basic. You're above 7, you're acidic. And again, that is opposite, as we see here, of our pH scale. Now, that does cause some problems for people. And the problem it causes is when they're asked this very simple question of, is the solution acidic, basic, or neutral? Sometimes people like to say it's acidic and basic, the same solution, and you cannot do that. I've never had anybody give me all three, acidic, basic, and neutral. So, but I've had people give me acidic and basic for the same solution. So there is only one answer to that question. And the reason why people do that is they calculate the pH and go, cool, it's above 7, it's basic. Then they calculate the POH and go, cool, it's below 7, it's acidic, and the same solution as both now. So my recommendation would be always look at the pH scale because that's probably the scale most people have in their head. Most people probably don't have the POH scale in their head. And I would always just look at the pH to determine if it is acidic, basic, or neutral. And again, should only be one answer for that question. Question on that there. Now, in addition, if you have the pH given to you, you can directly from it get the H plus concentration. And to calculate the H plus concentration directly from the pH, that's going to be the inverse log of the negative pH. Now, most people's calculators, when they hit the inverse log, that usually pops up at 10 and a caret, and then you want to go negative pH in that case. Or how some people incorrectly use scientific notation, which is why you're going to be in trouble if that's how you do it, because you will not get the right answer. By the way, if you have the POH, you can directly from that get the OH minus concentration. Exact same calculation, the inverse log of the minus POH, which again will put up usually a 10 and a caret and a POH negative. For most people to get to that button or to that version on their calculators, on most people's calculator, it is usually requiring people to hit the top left corner, either the second or the shift button. And usually the log button will have like a 10 to the X above it. So usually this, then that will get you the inverse log on your calculator. Questions on that there. So with that, you do have, like I said, some options as to how you could kind of do some of these answers. You may not even need to use KW. You could just use the pH or POH to get to the H plus concentration. You could still use KW if you still want to as well. Any questions? Yeah. Are you talking about on display? Yeah, to do this calculation. Is that what you're talking about? Yeah. Yeah. So if you had a display calculator, you would most likely hit either your second button or shift button and your log button, and then you would go negative and then your pH value. If you have a non-display, you have to go backwards on this one as well. So you got to go with your pH or POH number. Then you want to make it negative. Then you want to hit second or shift, and then you want to hit the log button. So that's it's not ln. It's the inverse log. So you got to hit the second and log button. That's the natural log. Other questions? All right. So it does, like I said, give you a few different ways to sort of do it. So why don't we try some here, just make sure our calculators work. We have a pH of 4.82. What is the H plus? What is the OH minus? What is the POH? Is it acidic, basic, or neutral? And for the bottom one, we have an OH minus concentration of 2.5 times 10 to the minus 7. What's the pH? What's the POH? What's the H plus concentration? And is it acidic, basic, or neutral? So give your calculator a test drive, see how you like it before you. Okay, let's take a look, see how you're doing. So on the first one, I do have the pH given to me. So from the pH here, I do have really two options since we're looking to solve for everything. I could get the POH from it directly. I could also get the H plus concentration from it directly. And in this case, I'm going to go with the OH minus concentrate, POH first. So we'll do pH plus the POH is equal to 14. So POH in this case would be 14 minus my 4.82. That's going to give me a POH, if I don't throw my calculator too far, of 9.18. Again, I could also get my H plus concentration from this. So my H plus concentration going to be the inverse log of the negative pH. And in this case, it should look something like this on your calculator, most likely when you punch it in, like so. And that will get you negative 4.82. It's going to get you a 1.5 times 10. Looks like 1, 2, 3, 4, 5 minus 5, I believe, here. By the way, going backwards, as we were just talking about, two decimal places gives me two sig figs. Yeah. So again, going backwards gives you that. At this point, you do have a couple of options to get to the hydroxide concentration. You could absolutely use KW like we did before. You could also do the same calculation with the POH, which is OH minus is equal to the inverse log of the negative POH. 10 to the negative 9.18. And that's going to get us here. Looks like maybe a 6.6 times 10 to the minus 10 does need a concentration unit of molarity in this case. Once again, you could use KW and you'll get basically the same thing. If you took this, obviously 1 times 10 to the minus 14 divided by it, maybe you get 6.7, a little bit different with a round, but pretty much the same deal. First off, any questions on any of those calculations? We want to know, is it acidic, basic, or neutral? This one is acidic, right? And pH is what we're looking at for that answer. All right, taking a look at the second one, we have the OH minus concentration given to us. So once again, directly from the OH minus, we could get the POH, obviously, and we could also get the H plus concentration. So in this particular case, we'll go with the POH first. POH is minus the log of the OH minus concentration. So that's going to be minus the log of, looks like 2.5 to the minus 7. To give us a 6.60 POH, to which I could very easily find my pH by simply subtracting 14, right? So I'm going to take 14 minus the POH to get to my pH of 7.40 in this case. Once again, two sig figs, two decimal places on those. What are we left with there? H plus. So again, if you want to throw back old school there, you can roll a little H plus and KW if you like. Minus 14 divided by 2.5 times 10 to the minus 7. And you got yourself a 4 with a lot of zeros. 4 times 10 to the minus 8 molar are obviously, because at this point you do have the POH. You could also use obviously the POH calculation as well. This one is going to be slightly basic. Yeah, it has 7.4. Any questions on any of those calculations? So most people struggle with, frankly, punching it in correctly in their calculator. Yeah, so make sure you know how to properly punch it in the calculator. Yeah. Any questions on that there? Yeah. All right, one more practice here. It's just calculate everything here by using KW. We can also just go right in and get the pH, which is, I think, what I'm going to do. So I can go right in using the H plus concentration there to get our pH. So 3.5 times 10 to the minus 6. That's going to get me here a pH of something. 5.46. Obviously, now that I have the pH, I can very simply find the pOH by simply taking 14 minus it. And that's going to get me a 8.54 in terms of our pOH. Again, I could also use KW to get the hydroxide concentration. Now that I have this guy, I could also do that the OH minus concentration is equal to the inverse log of the negative 8.54, and that's going to be something that looks like this. And getting, looks like 2.9 times 10 to the minus 9 molar. You obviously could also just use KW, right, as another option to do that. And then that's it, I think. And we're going to be looking at our pH value here, and it's less than 7. So this guy should be acidic. Yeah. Any questions on any of those calculations there? Okay, so you just want to make sure you know how to punch it in correctly. If you're having trouble, come see me. We'll figure it out on your calculator, probably. I imagine. All right, so let's talk a little bit about strong electrolytes. Electrolytes, as you may remember, are substances that, when they do go for a swim, uh, will basically 100% break apart into ions. They're not going to stay together. So you basically just have 100% ions in solution. So something like sodium chloride, if you have a sodium chloride solution, you no longer have any of the sodium chloride units together. You basically got a solution of sodium ions floating around and chloride ions floating around, and nothing completely together. Acetic acid over here is a weak acid. As you could also know from the reversible reaction arrows, we'll set up an equilibrium here. And a weak electrolyte, as you hopefully remember, is something that mainly will stay together in solution, but will produce a little bit of ions. So if you had a acetic acid solution, what you would typically have is acetic acid still together, but you will have a little bit of some acetate ions and a little bit of hydrogen ions floating around in the solution. And that's what, again, makes it a weak electrolyte. It's still able to sort of ionize, but will mainly stay together. Acid and bases are also strong electrolytes and weak electrolytes. There are some strong acids, which are strong electrolytes, will completely break apart, like hydrochloric acid here will completely break apart into H3O plus, and I'll put the H3O plus because the water's here, as it's going to send an H plus over, obviously, and going to make Cl minus, H3O plus, and a little bit of nitrate, H3O plus, and some perchlorate, and H3O plus, and some HSO4 minus in this case, right? So in terms of strong acids, there's really 6 strong acids that you come across, and that is hydrochloric acid, nitric acid, sulfuric acid, perchloric acid, hydrobromic acid, and hydroiodic acid. That is your big 6 of strong acids. Those are good ones to know for a couple reasons, because they are strong acids, but because there's only 6 of them, by process of elimination, it could also tell you what is a weak acid. So if it's not one of those 6, it's a fairly safe bet that if it's an acid, it's going to be a weak acid. So kind of knowing those are relatively an important type of thing. Um, in terms of bases, by the way, our strong bases again typically come from group 1 and 2 on the periodic table that have actually hydroxide in it, like potassium hydroxide, sodium hydroxide, calcium hydroxide. Again, for our strong bases, if you go group 1, lithium, sodium, potassium, hang a right-hand turn to calcium, strontium, and barium. Any of these guys, again, kind of hooked up with hydroxide, are usually going to be strong bases. Yeah, I believe that is correct, what you just said there. Yeah. So, for example, sodium chloride is a strong electrolyte, but it's not an acid. Yeah. So, yeah. But definitely, if it is a strong acid or a strong base, they would be considered strong electrolytes. Yeah. Other questions? Weak acids, on the other hand, mainly stay together, but do break apart a little bit. But again, here we're going to be sending our H plus over. We have our reversible arrow happening, and we get H3O plus and F minus, H3O plus, and a little nitrite, a little H3O plus, and some sulfate, and H3O plus, and a little hydroxide in this case. So these again are weak electrolytes. So if you had, let's come back here. You had a beaker of hydrofluoric acid. Again, you're going to just mainly have the hydrofluoric acid together. Will break apart a little bit, but mainly going to be that acid staying together. Our strong bases, as I mentioned before, again, group 1 and group 2 on the periodic table. Group 1 being the alkali metals, group 2 being the alkaline earth metals, and the word alkaline basically means basic. So that's where a lot of our strong bases do come from. And obviously, as you can see there, they produce hydroxide there on the right-hand side. They are strong bases because, frankly, you can think of it this way. They're kind of carrying the hydroxide with them. So as soon as they go into the pool there for a swim, they could just release it, and it produces hydroxide really quickly in the water or in the solution, and makes them a pretty strong base. Now, weak bases, on the other hand, are also weak electrolytes, so they will kind of stay together, not really break apart. But here we're going to actually have the water acting as the acid in this case, sending the H plus over. We'll make HF and hydroxide. We'll make here HNO2 and hydroxide. And probably the most common weak base that you'll see is ammonia. Ammonia is probably the most common sort of weak base that you come across. Going to accept the H plus. Going to make some ammonium hydroxide. In this case, as I might have mentioned earlier, a lot of weak bases are organic type bases. They usually have nitrogen in there, and carbon, hydrogen, nitrogen are a lot of the weak bases that you come across. Now, the relationship between an acid and its conjugate base, or a base and its conjugate acid, is an important sort of relationship to understand, and we definitely will see this relationship moving forward in this chapter. So the relationship between sort of an acid and its conjugate base partner on the other side of the arrow, are the base and its conjugate acid, is a opposite relationship. And what I mean by that is, we'll make like a little table maybe. If you have the acid on one side, and then that would be as partner the conjugate base on the other side. If your acid is a strong acid, its conjugate base partner will be considered relatively weak. And if your acid is a weak acid, it will create a conjugate base that's considered relatively strong. So it's sort of an opposite relationship between those things. Now, what does that mean? That means this, and we'll talk about it a little bit later on. If you have a conjugate partner, like a base here, the conjugate base that came from a strong acid, it essentially will mean that that conjugate base is frankly not going to continue to react with water. Water is present in solution, right? So there's water there. It will not continue to react. It is really considered a neutral sort of situation. If you have a conjugate base that came from a weak acid, that conjugate base will be relatively strong in the sense that it will actually continue to react with the water that's floating around with it. So it is strong in that sense. It is not as strong as like a strong base or anything like that, but it's strong in the sense that it's able to continue on. And this guy is able to continue on and react with water and have an effect on the pH of the overall solution. And we typically see this, as we'll talk about, with salt, a reaction known as a hydrolysis reaction. So if you can identify this sort of conjugate base as coming from something that's weak, you would anticipate it will continue to react with water and actually have a fairly good effect on the overall pH of that solution because of that. And this is, again, what is sometimes referred to as a hydrolysis reaction. Now, if you have a base, its partner will be a conjugate acid. And it's the same sort of relationship. If it is a strong base, it will have a relatively weak conjugate acid. So it will not really react with water or really affect the pH of that solution. If you have a weak base, it will produce a relatively strong conjugate acid, which once again will react with the water. So this guy here, much like above there, can react with water. And as we'll talk about how these guys affect the pH is, in this case, the base is going to accept the H plus, and ultimately what that's going to do is produce hydroxide in that solution. So it's going to have the ability to produce more hydroxide in that solution because it's present. And that's going to make that solution more basic because now you're producing a little bit more hydroxide. The opposite effect is here. If you have that kind of stronger weak acid that has the ability to react with water, it's going to send its H plus over to the water, and it will produce H3O plus, which will actually make the solution more acidic in its presence because it's going to be able to produce more H3O plus or H plus in that solution. So once again here, if we have a conjugate acid that comes from a weak base, it's relatively strong, but once again, not as strong as a strong acid. But when it's strong in the sense of being able to do these hydrolysis reactions and really affect the pH of the solution. There's a whole section we're going to talk about these reactions in this chapter sort of coming up. So that's a good sort of relationship to sort of keep in mind. Any questions on that? Okay. Here is a table from your book again, and you can see the opposite relationship. We kind of have increasing acids over here are strong acids, kind of as partners are going to be relatively weak, stronger bases, weaker conjugate partners on that side. And again, you can see a number of sort of weak bases have nitrogen sort of in there, and that's a very common sort of weak base. All right, so a strong acid completely breaks apart. A weak acid will stay together. So what happens if we are given the concentration of a strong acid and we're not given just a generic H plus concentration or H3O plus concentration? If it is a strong acid, because it's a strong electrolyte like HCl, so hydrochloric acid is going to 100% break apart into H plus and Cl minus. And if we know the concentration of the whole thing in this case, it is a 1-to-1 relationship between the whole thing and the H plus, which means we actually do know the concentration of the H plus concentration, and we could go right into our pH equation. So sometimes you may be given the concentration of a strong acid, And it may not just be a generic H plus or something like that. And if it is a strong acid, the good thing about most strong acids is they're mostly monoprotic, which means if you know the concentration of the whole thing, that is a concentration of the H plus. You could also have strong bases given to you, right? And if you had a strong base like sodium hydroxide given to you, it would break apart into a sodium ion and a hydroxide ion, right? And in terms of the pH here, the most important thing here would actually be the OH minus concentration. And if you know the concentration of this guy, it is a one-to-one relationship. You can figure out the hydroxide concentration, which will not give you the pH directly, but it will allow you to calculate the POH, right? And then you can subtract 14 and get yourself to the pH at that point. So you could also maybe given a strong base formula and a concentration and want to know what the pH of that solution is. And again, because it's a strong base, that'll give you your hydroxide, get you to your POH, and then obviously to your pH in that case. Any questions on that there? So why don't we try some here? What is the pH of 2 times 10 to the minus 3 molar nitric acid? And what is the pH of 1.8 times 10 to the minus 2 barium hydroxide? Take a few moments there, calculate up the pHs. Okay, let's take a look. So first off here, nitric acid is on that list of 6 strong acids. So that does tell us it's a strong acid. And because of that, it is going to be a strong electrolyte, which means when it's in solution, 100% going to break apart into H plus and some nitrate in this case. Again, 100% on this side. And since we do know that this guy's concentration is 2 times 10 to the minus 3, it is a 1-to-1 relationship between our H plus concentration, the whole thing, which means technically we take 1 times 2 times 10 to the minus 3 molar, gives us 2 times 10 to the minus 3 molar is our H plus concentration. And the pH in this case minus the log of 2 times 10 to the minus 3. And that's going to get you a pH here of 2.7, I believe, in this case, which is acidic, which is good since that's an acid. So that would be good. Yeah. Any questions on that calculation there? Bottom, that is a base. That is a strong base. Again, it is in that region of group 1 and group 2 where we kind of go this way. And again, that kind of group 1, group 2 sort of move with hydroxide. So it is going to be a strong base. And that means it also will completely break apart here. And going to give us a barium ion and is going to give us a couple of hydroxides here. In this case, 1.8 times 10 to the minus 2 molar. We are interested in the hydroxide as that's going to allow us to get not to the pH, but to the POH first. It is a 1-to-2 relationship. So how concentrations are affected, you take 2 times the concentration in this case to give you the proper hydroxide concentration, which looks like it is here, not that, 2 times 1.8, so minus 2. Looks like it is 0.036 molar. That's going to roll into our POH. And that's going to give us a POH of like 1.44. Now, obviously, at this point, all we have to do to get to our pH is take 14 minus 1.44, 1296 maybe, 1256 here. Yeah, I'll write it right, maybe 12.56. There you go. This one is going to be definitely basic because it is a base, right? And this one obviously was acidic because it is acid. So you can see here, and I would say probably in most cases it's going to be your strong base. You might have to adjust the concentration, especially if it's a strong base from group 2 on the periodic table. It's not, again, a one-to-one concentration or one-to-one relationship. Yes. Correct. And you do have to adjust it. So um, that's how sort of concentrations work from like on compounds to their ions, because basically what you're doing is this. That's the shortcut calculation by just multiplying it by the coefficient. If you did sort of the longer version of that calculation, it's basically just this, and um, so you basically have 1.8 times 10 to the minus 2 moles per liter, right, of barium hydroxide, right? And basically what you're doing is just the mole to mole relationship. It's a 1 mole to 2 mole relationship. So that is where the 2 moles of the hydroxide come in to 1 mole of the entire thing. And this counts out the whole thing, and you basically end up with moles per liter of hydroxide. And that's basically why we're multiplying by the 2 in this case. So the quick way to do it is basically whatever the coefficient is when it breaks apart, you just multiply the concentration by that coefficient. And that's because in this case, there's basically twice the concentration of hydroxide ions floating around for every barium. So the barium concentration in this case is basically 1.8 times 10 to the minus 2. So if you just think about when it goes into the solution, you get basically 1 barium ion to 2 hydroxide. So you got twice the concentration of hydroxide in that solution as you do barium. Yep. Other questions? All right, so here's the table of those guys. There's strong bases, there's strong acids. And again, those are good ones, obviously. Just kind of have and know. It'll kind of help you out. Let's talk about weak acids and how we basically deal with pH of weak acids, and eventually we'll talk about weak bases. Unfortunately, weak acids and weak bases are not as straightforward as strong acids or strong bases, and that is because they will set up an equilibrium. And because this weak acid here, call that our weak acid, it's going to set up the equilibrium. It's going to, again, send its H plus over and make our H3O plus and so forth. Because it does so like anything else, we could write our favorite thing ever, which is an equilibrium expression for it. And we could take the water out and just show the weak acid dissociated into its ions, setting up his equilibrium here. And we take our products over our reactants like normal, and we get a Ka value to add to our ever-growing list of K values. We've got Kp, Kc, Kw, Ka now. A for a weak acid, and it is still an equilibrium constant no matter what the little letter on the bottom is. Products over reactants like normal, we still don't put anything that's a liquid, right? Anything that's a solid in there. And that is a weak acid dissociation constant. And the relationship of this is the higher the Ka value, the stronger the weak acid is. So it is still a weak acid, but in comparison of one weak acid to another, the higher the Ka value is, the stronger that weak acid is compared to the other. It is nowhere near as strong as a real strong acid, but a weak acid can do that comparison. Why is that comparison made? Well, the one thing we know about equilibrium constant values is hopefully if I have a large value of K, when I reach equilibrium, do I mainly have reactants or products? Large value K means you have products, yes. And on the product side here, I see an important guy. I see free H plus, right? So the larger the Ka value, that would mean in this case, you would have more products, which means in this case, your acid's able to produce more free H plus in that solution, even though it's a weak acid. So that is why a larger Ka value would mean it's a stronger weak acid. A smaller Ka value would mean that it's a weaker weak acid in comparison. Any questions on that? Would I expect to find a Ka value for a strong acid? I will not find a Ka value for a strong acid because what does a strong acid do when it goes for a swim? Stay together or break apart? Completely breaks apart. It does not set up an equilibrium. Hence, because it doesn't set up an equilibrium, There is no equilibrium constant, right? So there you go. So that is also a really big hint that if you see in a problem a Ka value with an acid, it is a weak acid, right? There's no doubt about it. Or you can find it on the Ka table. So strong acids will not have Ka values because they really don't set up equilibrium. Strong acids are one-way streets, right? They're all dumping out over here to ions. Nobody's coming back the other way. The only strong acid you will probably ever find, maybe in most cases, on a Ka table is sulfuric acid. It's the only one that you may find on a table. And the value that you get for sulfuric acid is it's a large value. Not really a number. It just actually just says large, right? So that's not a very helpful number or anything like that. The reason sulfuric acid sometimes are found on Ka tables is because it's a diprotic acid. And the second part of sulfuric acid is a weak acid. So that's good. That guy will be on the table with an actual number, but sometimes you may see sulfuric acid, and usually they'll just say it's large, which obviously means nothing to worry about its Ka value. Any questions on that? Now, how do we find the pH of the solution? Well, because it's a weak acid, it's an equilibrium. I'm feeling like, this is like an ice table situation. Yes. Again, you probably can't go wrong in this class with an ice table. And you would do an ice table in this situation. You would be interested in this case in the H plus concentration. And the only real main difference usually between these type of problems and just a regular old equilibrium problem is usually in these type of problems you're interested in the pH. So you got to just take that extra step at the end. And once you figure out the H plus concentration, put it into the pH equation, basically. pH is equal to minus log of the H plus, and that's basically the additional step. Also, because in a lot of cases, I would say most of the time when you do solve for X in your table, I would say in most cases your X is going to be your H plus concentration. And like if we did an ice table on this guy of breaking down into H plus and A minus, and we had initial concentration 0, 0, minus X plus X plus X, initial concentration minus X and X. As you can see, in most cases, your X is going to be your H plus concentration for a weak acid. And at that point, all you have to do then is go into your pH equation and you'll be good to go. So a little extra step you have to do because it is a weak acid. Any questions on that? You can solve this just like any other equilibrium. You can make an assumption. You can give it a go. You definitely want to make sure you check it because in some cases it will not work for sure. But if you could do it that way, R quadratic, you probably will not find too many perfect squares here in a weak acid situation, but it's going to be either one of those two, assumption or quadratic, to sort of solve it. Here's a table from your book there, and again of some different Ka values. You might need a reference for problems, as they may not give it to you in your actual book there. And again, I could see some of those. Why don't we give one a go here and see what happens? What is the pH of a 0.5 molar HF solution? The Ka value is 6.4 times 10 to the minus 4. So basically just work it like a normal equilibrium type. Okay, since we're getting to that, let's take a look at it here together and sort of see what we need to do. Once again, a couple of things that help me understand what I should do. I see HF, which is an acid. I also see, again, a Ka value tells me it's weak. Weak should then tell me I should do myself an ice table here. So I'm just going to simply show my HF dissociating into H plus. And again, if you want to use the water and H3O plus, perfectly fine. But I'm just going to do it this way. I do have my initial concentration of my HF, which is 0.5. These guys, again, is going to be 0 since there's no mention. We could, again, safely assume it's heading in this direction. So we're going to go minus X, and plus X. That means at equilibrium 0.5 minus X, X, and X. Any questions on the ice table here? We can use our Ka expression because it's an acid of our products over our reactants, and that's going to equal my 6.4 times 10 to the minus 4. Like a normal equilibrium problem, we're just going to put everybody into that expression, basically solve for X, right? So when we do that, that's going to give us x squared over 0.5 minus x, products over reactants, equals 6.4 times 10 to the minus 4. That is a small value for k, which means I can try my assumption and assume x is equal to 0. Remember that when you do the assumption, it is only the x's we're really subtracting or adding to a number. So that's going to reduce this down to x squared over 0.5 is equal to 6.4 times 10 to the minus 4. I'm going to multiply, and then after I multiply, I'm going to take the square root. So one right after the other. So we can go 6.4 to the minus 4 times 0.5 and hit equals, and then take the square root. You got something like 0.00032. Going to take the square root of that, and that's going to get me an x value here, 0.0179, we'll call it at this point. First off, any questions on that there? Remember that if we do the assumption, we do need to check it. So to check our assumption, we're going to take our x value, we're going to divide it by what we're going to subtract it from, the initial concentration, and times it by 100%. And if I do that in this particular case, all right, double did the double square rooted it there. All right, divided by 0.5 times 100. Looks like we're looking at 3.6%. So the check here is okay. So because that check is okay, we can see from our table that the X does equal the H plus concentration. So basically, this is going to equal our H plus concentration. And that's really what we're interested in here since we're looking for the pH. So the pH will then be minus the log of the H plus. And that's going to be minus the log of, it looks like 0.0179. Whoops, 179. There we go. And that's going to be minus the log 0.0179. So 1.75 pH in this case. Question on that calculation there. It is acidic, which is good since this is an acid. So that would be good. If I end up with a basic pH, not so good, probably. Yeah, that's good. Any questions on that there? All right, we're going to leave it there for